Hey, thanks for your patience. So my name is Ville. I'm here with two colleagues of mine, Ravi and Savin, and we are here to talk about machine learning infrastructure that we have been building at Netflix. Well, first, when I mention machine learning and Netflix in the same sentence, the first thing coming to mind to many people is the recommendations. So when you go to netflix.com and like you see all the TV shows and movies, as you may know, those are the ordering like of what you see is created by a machine learning algorithm that like tries to decide like what you might want to watch on your Friday evening. Well, now the interesting fact is that the recommendations are kind of like a tip of the iceberg of all the machine learning efforts that we have ongoing at Netflix. So it's kind of really the crown jewel, but there are so many other things that we are doing with machine learning today. So for instance, like we are using natural language processing to understand the screenplays, what's going on in different scenes. We are using computer vision to understand the actual video content. And let's say we are using even machine learning to optimize how we place the content to our content distribution network, so you never have to see the spinning wheel while you are watching something. So it's really like tens, if not hundreds of different machine learning use cases that we are dealing with at Netflix today. Well, now, like we are here, like from a machine learning infrastructure team, like as it says on the T-shirt, and the challenge for us is that, like as you saw in the previous slide, we are dealing with tens of different use cases, and now it's very hard to build common infrastructure like for such a heterogeneous set of different use cases. So, like we can't just say that everybody must use TensorFlow, and we can't say that like everybody must use this framework, but like we must be able to accommodate really a wide array of different kind of things. And now, when this team started about 2 years ago, we asked ourselves the question that, okay, so what is common? Like, what is fundamentally common to all these machine learning workflows? And starting like from the very basics, one like thing that's absolutely common to everything is that, well, everybody needs data. So everybody needs access to data somehow. And we have a data warehouse that's based in Amazon S3, and that works really well for us, as my colleague Ravi will be talking later in this presentation. Well, now, on top of data, you want to perform some kind of a compute. You want to take the data, you maybe want to train a model, maybe you want to do some data processing. So you need some kind of a compute system. And like, for instance, you could be using Kubernetes just to farm out the compute to kind of computers and like burn some CPU cycles. Well, so it happens that these machine learning workflows aren't like just a single step, but typically there are multiple steps involved in the whole end-to-end machine learning workflow. It might be that the first step is about getting the data, maybe the second step is about feature extraction, then you train model, maybe you train multiple models, then you gather the results, all that stuff. So you need some kind of a way to orchestrate all these steps. And now, for instance, you could be using Apache Airflow or other DAG schedulers to kind of keep everything going. So, well, now the next question is that, okay, so how do you actually perform the compute? Like, how do you actually express like what you want to compute? And now, oftentimes these days, people encapsulate their workloads as a Docker container. Like in a Docker container, in an image, you can have your source code, you can have all the dependencies and so forth, and then like the Docker goes to Airflow, Airflow schedules it like via Kubernetes, you get the data from S3 and so forth. Well, technically, that looks pretty good, except for the fact that you never deploy a workflow only once. You keep iterating on these things over and over again. And now to keep track of like everything you have done in the past, you need some kind of a versioning system. You need to know what kind of experiments you have run in the past. You need some kind of versioning for your source code as well. And now there's the question that where does the source code come from? Like how do you write the code? Of course, I mean, you could be using your favorite IDE, like maybe Vim, maybe Emacs. But if you're a data scientist, there's a good chance that like you want to use, let's say, Jupyter notebooks. And now, and like since probably many of you were in the Peter Norvik's like keynote this morning, he also referred to the fact that interestingly, the actual machine learning is just the tip of this like a tall stack of different things. It's kind of almost paradoxical that on the T-shirt it says ML infrastructure. I guess it's really cool these days, but the fact is that there's a thick layer of other things, other considerations that you have to do to make the machine learning pipelines actually work end to end. And now a particular challenge that we faced and our data scientists face at Netflix is that if they had to navigate this space by themselves, imagine being a data scientist and you have to deal with Kubernetes, you have to deal with Airflow, you have to deal with Docker, you have to deal with versioning. How do you even version notebooks? It would be impossible. And this was basically the motivation for a library that we have been building internally called Metaflow. And it actually says on the back of my t-shirt. So please come to us like after the presentation if you have any questions. And like what we wanted to do with Metaflow is to provide a unified single interface to the whole stack end to end. So you can access the data from S3, you can perform computation without even thinking about it, and like you have nice integration to notebooks, and then you get to choose exactly the machine learning libraries that you want to use. And especially what we didn't want to do is that we didn't want to reinvent the wheel. We didn't want to reinvent the orchestration layer. We didn't want to reinvent the Docker management or the kind of container management layer. None of that. But we wanted to have a unified, vertically integrated experience that takes all these like great systems that are already out there and provides a unified view to the data scientist. Well, now, I don't know, hopefully this is not disappointing, but actually like we are not planning to talk about how to run data science on Metaflow today. Instead, this being a Python conference, we thought that, well, I mean, wouldn't it be cool if we shared some experiences that we had building this Python library? So Metaflow is pretty much like all in Python, and there are like some like really high level good ideas that like we figured out as we were building the library and like as we went about creating this library. So we will be sharing these learnings with you today. Well, now the thing is that there's going to be a lot of information, also 3 different faces on stage, which is always kind of strange. So there's going to be like so much that like please come to us afterwards if you have any questions. You can recognize hopefully the t-shirts. So we are happy to talk about all this stuff. And now the first of the 5 things that like we want to share with you today is this idea of having a functional core and an imperative shell. And this phrase is not invented by me, it's not invented by us. It's actually, if you Google for it, this has been around since at least 2012. There are many great presentations about the idea. It also goes by another name called the clean architecture. There's even one called the clean architecture in Python. Like there's a presentation, it's pretty good. So you should take a look. And the idea is that like, how do you actually go about designing and building and architecting a complex library like what we did with Metaflow so that it's somehow manageable? And the basic idea is that, okay, so first, I mean, you should be always asking yourself that, okay, so what are we even trying to accomplish? And in our case, we wanted to accomplish a system that would help data scientists to take end-to-end workflows, take like a data science project, like from all the way from prototype all the way to production. And we wanted to build something that like supports like a complex undertaking like this. And now in a very abstract sense, of course, like you could view the machine learning workflow, the whole thing end to end. I mean, it's a function. You put some data in, some data comes out. And now one, like a very desirable characteristic of a function like this would be that it would always work the same way. When you put the same data in, you get the same results out. And like one really nice thing of like functions like this that are side effect free is that like they are reproducible. You can debug them really easily. And now, in our case, the function is basically, you can kind of consider that the one function is just like a big honking DAG. It's the whole thing, like kind of getting the data, running some compute, like sending it somewhere. So many steps, so it's kind of really like a monster function. But it would be nice if we could somehow consider that it's still idempotent. Now, on the other side, like, well, I mean, the function only produces same outputs if you give it the same inputs. So again, now Netflix produces tens of billions of data points every day. So of course, like data is not static in any ways, but still we can model it as these like immutable artifacts, which is a very good idea. In our case, like we can just consider that these immutable artifacts, so snapshots of data, are just some maybe files in the cloud. So now about the idea of like, what does it mean to have this functional core and an imperative shell? Well, now at the very core, you can take the kind of the very core concept that is central to your project. And in our case, that is that of a DAG. You have a graph. And now you can imagine building a Python library that has very nice functionality for traversing the graph and like maybe listing the steps, listing the edges, all that stuff. And the nice thing is that can be very functional. It always performs the same way, no side effects, like none of that messy stuff. And like you can imagine that like testing a library like this would be very pleasant. So you can even like have beautiful model-based testing for this and make sure that it always works correctly. Now around this, you want to model the data. And in our case, the key part of the idea of having this functional core and imperative shell is that you model the data as these like values rather than having a stateful object. So instead of like dealing with stateful databases, you just like get these immutable artifacts in your system. And again, like when you have a immutable data, you have your DAG, you can again, test everything, make sure that like everything works in a reproducible manner. around this, like as I mentioned in the stack, we are very much concerned about the versioning and like keeping track of everything that like ever gets run. We want to know the experiments that are run in the past and so forth. So we have this layer of metadata where people know, I mean, like all the experiments that have been done in the past. And also, well, the part what is not fully immutable is that you can even afterwards go and tag something that, oh, by the way, these were the good results and these are the bad results. And above this, now we start like moving to a kind of a more like kind of a messier, higher entropy world, which is the world of like integrating with these systems like, let's say, Kubernetes or like Amazon S3 and so forth. And of course, those systems have all kinds of side effects. But I mean, like we can still like try to kind of keep it as pure as possible. But now, I mean, like what is really, really important and like what is really like dear and to our hearts is the question of this user-facing API. And the fact is that our users absolutely love building code in Python. Our users are data scientists who use Jupyter notebooks, other ways to kind of use libraries like TensorFlow and PyTorch to model their like machine learning workflows. They want to use Python. And now the question is that like, should we design the delightful API so that it is really pleasant to use for the users, or like so that it really nicely aligns with the functional core? You could imagine having a really nice machine learning library that, let's say, allows you to express your matrix factorization as monads, and like you could probably write your PhD about it, but it might be hard to use like for like normal human beings. And that's why we decided that like we are going to make even technical compromises if it makes the API easier for humans to use. And it even like in some cases it's maybe technically not quite as elegant as well, as long as like we can make data scientists more productive with it. So the idea here is that, well, now as an engineer, you might think that, well, I mean, we don't want messy APIs, everything becomes fragile and hard to operate. But thanks to the fact that we have this very robust functional core, we can have this kind of a messier imperative shell and still keep things manageable. And now, this being a Python conference, I want to highlight that especially these outer parts are really a good fit for Python. So Python is an excellent language for building a very human-centric, very like easy to use APIs. Of course, users love to use Python. Integrations are pretty nice to handle in Python as well. Arguably, you could build these core parts in other languages, but Python is just good enough for that as well. Just to give you a taste how it looks like, is that our principle is really that like we want to kind of make the framework as easy to use as possible. We don't want to impose any new paradigms, no new frameworks, none of that stuff. In the best case, you can just copy-paste your existing messy data science code, and it just works. To kind of just add a bit of like extra syntax here, you can model your DAG as a single class where nodes of the graph are just these methods decorated with the step decorator, and the edges of the graph are just these self.next transitions. And then like you can do whatever you want in the Python code. And now the nice thing about this is that, well, I mean, like we can infer this DAG out of your class. And there are many benefits now to having this DAG. And like colleagues of mine will be talking more about that. And I will leave the stage now for Ravi, who will be talking about scaling up and out. Thanks.
Hello, everyone. I'm Ravi. Thank you, Ville. We probably all heard of this word, scale. And while it probably means different things to different people in different contexts, I am going to talk about it in the context of compute and resources. I would like to share our perspective on why we recommend scaling up and out as a good idea to all our data scientists. To set the stage for the next few slides, I thought it might be easier if all of us had the same problem with some numbers to grapple with. Before that, how many of you have watched our beloved Stranger Things 3 that released last July 4th? Okay. Did you love it? Anyway, I couldn't help but binge watch it. But anyways, hypothetically, imagine that one of our data scientists decided to go and predict the viewership numbers for a show like that so that we could improve our content catalog. Let's approximate the subscriber base to be 150 million subscribers, probably slightly higher than that. This data scientist wanted to decide if one giant model to rule them all or per country models, which one might do better. Also, let's assume a kilobyte per row, maybe 1,000 columns, 1 byte each. And this puts this whole data frame maybe over 150 gigs if you had to load it all into memory. While 150 gigs might seem quite a bit to load into your laptops, It's actually not that bad if you look at some of the big machines that we have at our disposal nowadays with cloud providers like Amazon with AWS and Google with GCP. Here in the slide, I pulled some numbers from Amazon about the EC2 instances with the largest easily over 500 gigs and over 64 CPU cores. Therefore, scaling up or vertical scaling, where you actually add more resources into your existing machine, in my mind, is a good idea always to start with. I say this because most data scientists then don't have to deal with a lot of complex interactions with distributed systems and multiple machines, etc. Also, loading into memory is probably one of the easiest and fastest things to do compared to other scalable infrastructure solutions. You can easily prototype something with a small data set and then quickly scale to much larger data sets thanks to the virtue of scaling up. So here's actually how easy we make it for the data scientist with Metaflow. We have a simple @resources decorator that you can see on the second step, where you can specify compute resources like CPU, memory, GPU, etc. And leveraging our compute orchestration layer, we can get their code to run on the best machine for the constraints. Also, some of you might be skeptical. Like, Netflix probably has a lot of money to own some of these big, beefy machines. What about us? Well, cloud providers also have a pay-per-use model. So you can actually get just this one tiny step to run for a few seconds or minutes, as much as you want to use it, and then just pay for that, which makes it quite accessible for everyone. But wait a second. We also said we want to generate per-country models. So while scaling up would mostly get you to probably do the one giant model, if you wanted to do all the per-country models, we might either have to produce them sequentially with a for loop, mostly because you might run out of RAM having all the big data frames for all the countries. Thus, it might be unavoidable and sometimes necessary to think about the other kind of scaling out, or horizontal scaling, where you add more machines to your pool of resources. Also, it might be one of the easiest ways to introduce parallelism into your workflow to get things done quickly. So within Metaflow, we actually provide a simpler version of horizontal scaling, which is we let you just distribute mutually independent set of compute, leveraging something like a for each. So in this example, you can specify the countries as a list in Python over the countries you want to generate the per-country models on. And then you can specify the step that you want the for each over, so in this case, train. And then Metaflow takes care of spinning separate tasks with the appropriate parameter for the user. This works quite well for the problem at hand, because generating per-country models, the one for the US, probably has nothing much to do with the one for India. And the same concept could also scale to other things, like a hyperparameter search, for example. I already alluded this to a little bit when I spoke about AWS, and how the cloud is actually making it quite easy to farm off compute. But it also has so many other good goodies to offer. At least we at Netflix are cloud first and love the cloud. Switching gears from compute, I want to talk a little about data and storage. Haven't all of you had that experience while debugging some issue that you wish you had all the parameters, maybe the code that was running at the time of the crash? Wouldn't it be great if you could store everything? Ville spoke about how we love building on the top of shoulders of other great infrastructure instead of reinventing the wheel. And one such great piece of infrastructure that we, within Netflix MLI, love is S3, or Simple Storage Service. And I want to show you how it helps us store everything for improved reproducibility for our users. S3 is a simple object-based storage system. What that means is you can have as many buckets as you want that contain objects with a user-defined unique key. And We actually play a couple of neat tricks for storing everything on behalf of our users within Metaflow, like that big pandas data frame that you saw in some of our previous example. What we do is this. So imagine you have your pandas data frame. We first want to serialize it to some bytes. You can probably leverage something like Pickle. It mostly works in all cases, but sometimes not. But you can always use other serialization libraries, and then compress them with excellent libraries like gzip or zstd. That hugely reduces our storage footprint and thus our cost. Another useful trick is that we make the data content addressable. And what this means is we compute the key as the hash of the value, maybe using something like SHA-1, so that we can prevent storing the same data multiple times on S3 in case our users' flow didn't actually change for that specific data. All of them combined actually make it quite affordable for us to store everything in S3 on behalf of our users. The infinite elasticity and the pricing structure already makes S3 a great proposition for us, but I want to convince you one step further. I know some of you might be thinking about performance, so I want to talk about the amazing throughput that we actually do manage to get from S3. While the latency might seem slightly high, 20 milliseconds for metadata queries and probably 100 milliseconds for get or put, the throughput can actually be pretty high. We see upwards of 10 gigabits per second or more. To achieve this high throughput, though, and to make it really easy for our users to access S3, we ended up writing our own client on top of libraries like Boto to talk to S3. Our client obviously provides some of the basic access to let you get objects, put objects with some value, but also models good concurrency design by allowing bulk access like get many and put many. And what's nice about this is that way the user can tell us all the work that they want done, and we can decide how to achieve parallelism for their workflow. Also, in order to achieve the high throughput, we actually keep multiple concurrent connections open to saturate the network bandwidth because we feel like a single connection was insufficient to do so, and then leverage multiple processes, hopefully in Python, to drive the parallelism. So on that note, let's quickly look at our options when it comes to concurrency in Python to feed those multiple concurrent connections. So here on the slide, I have the options that most of you might be knowing. Also, I want to really quickly mention this great talk by Rob Pike about how concurrency is not parallelism, which I will not attempt to explain today. But suffice to say, concurrency is a way to build things. It's the composition of independently executing processes in the abstract sense, while parallelism is the simultaneous execution of these processes. I'd like to therefore think model for concurrency, parallelism, may come. Each of the three things on this slide all have their place, and if you know when to use them. Within Metaflow, we actually leverage all of them. Multi-threading for decoding Parquet chunks in parallel. Multiprocessing is the backbone of that high throughput client that I spoke about, and also to parallelize those task processes. And async IO is used in our microservice architecture. But quickly going through each of them, multi-threading is great for IO-bound workloads. And you could probably use something like the threading module or the thread pool executor. But you have to remember the global interpreter lock, which might prevent parallelism if you just apply it blindly. Multiprocessing typically works well in most scenarios, especially CPU-bound workloads, allowing you to spin up a new Python interpreter, thereby working around the lock. And for this, you can mostly leverage the subprocess module or the process pool executor. There's a slightly higher overhead just by spinning a new process, maybe around 20 milliseconds or so, but definitely works well in throughput scenarios. And for posterity, I also want to cover async IO, which is Python's answer to cooperative multitasking, which might be more lightweight than multi-threading, but and it only works with Python 3.5 or greater. But I feel the biggest challenge is it's hard to get it right, but if you do, we'll probably get the gains. With that, I want to hand it over to Savin to talk about a few other good ideas we have for you. Thank you.
Thanks, Ravi. So earlier in this talk, you heard about how to reason about your machine learning flows, some of the scaling challenges that we have encountered, and how scaling up or out, depending on the context, could be a nice little strategy. Another equally important thing is how do you guarantee predictable experience to your users? And that's where reproducibility becomes increasingly important, right? Like, to put it simply, if, let's say, I have a piece of code, I want to make sure that I'm getting more or less the same results, the expected results, every single time I execute, no matter if I'm executing it today, 2 months from now, 2 years from now. And one way of achieving that is by making sure that reproducibility is treated as a first-class concept in any of your machine learning systems. And once we get there, reproducibility actually unlocks a few more benefits for us. It fosters trust. Now you can take anybody's code, and you can recompute the results, the outputs that they promised that their code generates, and you can verify those. It also fosters collaboration, because now you can take, again, anybody's code, build on top of that, and sort of like get some reliable behavior out of that. So if we dive a little bit deeper into the notion of reproducibility at the end of the day, it's indeed a spectrum, and it's really important to understand that and know, depending on the business context, depending on your particular operating context, where would you want to lie on that particular spectrum. So let's take an example. On one end of the extreme, you have your model. It could be just a simple dictionary of coefficients. It works well in many cases, but it's not at all reproducible. If you lose that model, if somebody comes to you and asks you to recreate that model, you'll have a really hard time. So maybe you want to store the code that generated that model, right? It'll get you a little bit closer to some notion of rerunnability, but still it's very far from true reproducibility. You might want to introduce some sort of model management system, some sort of experimentation tracking system, or Git-based version control, something that sort of like allows you to keep your history of changes somewhere, so that you can go back in time, you can figure out like what sort of changes did you introduce over a period of time, and reason about the state of the system. But that still doesn't really get you all the way out, right? Like, machine learning code, by its very nature, the results are highly dependent on the execution context. What sort of infrastructure were you executing on? Were you executing on CPUs, GPUs? Was there any kind of acceleration involved? So there is an increased need to sort of like capture that metadata as well, which is often not really part of any of the user code. Now, another big aspect that is often lost in many machine learning systems is the notion of libraries, right? So you might have your TensorFlow code or your PyTorch code, and transitively it might be pulling in gazillions of different dependencies which are evolving over a period of time. And to maintain any notion of explicit reproducibility, you need to understand, you need to log and track what exact dependencies were involved when particular results were generated. And the other half of user code is the data in itself, right? Like, if your data is mutating over a period of time, then if you have to go back in time and triage certain issues, but if you have lost that data, then all bets are off. It's really difficult to triage any issues and go beyond that. And machine learning systems, by their very nature, there's an inbuilt entropy in the way they behave. There's some amount of statistical randomness, which makes machine learning awesome at the end of the day, but then it makes our life really difficult, because it's really, really intractable to actually capture that in any reasonable manner. So as you can see, as we go towards the holy grail of reproducibility, it becomes increasingly harder and harder from an infrastructure perspective to offer increased guarantees around this. When it comes to Metaflow, we sort of like chose to lie on the right extreme of the spectrum, where we place certain assumptions around the nature of the data. We assume that because we are operating in the cloud and we have infinitesimal storage capacity on S3, we can assume that the input data that the users are giving us, they are immutable snapshots. And if we just persist data pointers to those snapshots and then take care of everything else, then those provide a really nice guarantee to our users, which in our observation has worked out really well for us. So in practice, this is what our execution model looks like. So on top of any container orchestration platform, we execute what we call a Metaflow execution unit, which wraps around the user code, the metadata that was involved that we sniff from the execution environment, a manifest that contains all the library dependencies, defined either explicitly by the users or transitively pulled in, as well as data pointers to all the snapshots that are being stored in S3. Another thing that we wrap in this execution unit is the Metaflow code in itself, because our environment, our infrastructure is also evolving over a period of time, and we want to make sure that our users don't suffer a hit in any sort of reproducibility guarantees as we push out more and more changes into our execution infrastructure in itself. Now, when it comes to the library manifest, we had a bunch of different options here, and as part of this talk, I would love to share some of our learnings when it came across, like, okay, how do we manage these library dependencies? What sort of dependency management solution do we bake into Metaflow? Since we are at a Python conference, most of our users also use Metaflow in the Python world. One of the most obvious choice that pops up immediately, hey, why don't you use pip with virtualenv? It's an amazing solution, but it has a few deficiencies when it comes to actual machine learning application. Machine learning code, by its very nature, it has dependencies not just in the Python world, but also in the non-Pythonic world. And pip can provide you isolation when you are squarely in the Python world, but as soon as you are depending on any of the system packages, then you sort of like lose any sort of isolation guarantees. It's not at all language agnostic, so specifying any specific system package becomes highly non-trivial. But it has a really low overhead. Most of our data scientists, most of our users are already familiar with the ecosystem, so defining any sort of dependencies becomes really simple and straightforward in this particular pattern. Another alternative that a lot of other machine learning systems that we looked at use is using Docker as sort of like an orchestration substrate, as well as a packaging module. It provides amazing runtime isolation because it relies on process level isolation on top of OS kernels. It's language agnostic, but it doesn't really come with low overhead. Writing reproducible Docker files at the end of the day, it's highly non-trivial. You're still not solving the problem of what dependency management solution to use, what package manager to use, and it's really cumbersome. Ville spoke a little while ago about how we represent a machine learning code as a DAG. And because we have this notion of DAG, what it means is that we can execute every single node of that DAG in isolation. So theoretically, they could be running in different execution environments. And in that sort of an execution model, Docker essentially isn't something that we would refer to as a low overhead construct. So our solution, our dependency management solution, essentially builds an ecosystem around Conda. So Conda is an open source package management as well as an environment management system, which has an amazing open source traction in the data science community. So most of the Pythonic packages are present in the Conda ecosystem, as well as all of their Pythonic and non-Pythonic dependencies. And we have found it really simple and straightforward for it to integrate within our systems as well. This is one very small representative example of how we have integrated with dependency management as one of our solutions. So in this example, you can see that we have like 4 different steps. The workflow starts at start, we prep some data, train a model, and then we finish. The prep step essentially runs on the user's instance with no other dependency except for pandas 0.25. The train step, it runs with no other dependency except for TensorFlow GPU, the specific version being 1.14. And it runs on an instance that is hosted on the cloud with 4 GPUs, and then we bring back the results to the user's instance. So to them, it's really transparent. To our end user, it just feels that they are running on their box with all of these environments just managed behind the scenes for them. Now, what we are doing behind the scenes when a user starts to execute this flow is we actually inspect all the dependencies that they have specified, and we capture the entire dependency graph. Because when you're resolving these dependencies, the actual dependency resolution process, it's not really idempotent, right? If I import TensorFlow today versus if I import TensorFlow tomorrow, the transitive dependencies that it might pull in would be different, which means that the way your code might behave would be different. So when the users execute their code, we actually capture the entire graph. We capture all the explicit packages using our high-throughput S3 client. We actually store everything in S3 for posterity so that if packages go missing upstream, our users will not even miss them. So what it also allows us to do is when users have to move their machine learning models into production, let's say schedule it using a scheduler like Airflow, we can just take the exact Metaflow execution unit that we have already bundled and just move that into production. And it inherently then guarantees that the behavior that they were observing when they were executing their process locally is the same behavior that they observe when they are in production. So you've seen me talk about, over the past few minutes, my other colleagues and I, we have been focusing on making sure that our users have access to delightful APIs and effortless UX. And that has indeed paid us, it has indeed paid off really well for us in terms of user adoption that we have seen. So while we were building Metaflow, we sort of became aligned with some of the tenets, our own version of the UX honeycomb that we relied on while figuring out what sort of features to push and what should be our overall philosophy around the user experience for our end users. And we came up with some sort of ideas which I think would be useful for any productivity-oriented tool that people might want to build. The core amongst that is that we need to make sure that our system is usable, people find use for it. Metaflow, for example, it's built in Python. Our data scientists, they use Python. So the curve of usability is really low. They use constructs that are indeed very natural to them, like decorators and functions and all of that. We have to make sure that it's indeed addressing a useful use case. We need to make sure that our users, at the end of the day, they want to make sure that there is some system which sort of manages the entire life cycle of machine learning systems for them. So there's a clear need that is being addressed. We need to provide consistent interfaces. Most of the goodies, most of the features that we expose to our users are exposed using decorators. We provide a seamless experience at the end of the day where, if you have to, the way you execute locally is the same way that you execute in production, and when you have to graduate your projects, it's a very, very seamless experience at the end of the day. It's also really important that the users trust the tool that they are using, and as such, transparency becomes really important. They need to be able to reason about what the tool is doing on their behalf. So we rely on copious amounts of logging, making sure that Metaflow fails very loudly when there are any issues. We also make sure that it's very lightweight. Metaflow is a pure Python package with very minimal set of dependencies, so you just do a pip install or a conda install, and off you go. And the really important point for us from a usability perspective is to make sure that whatever tool we put out to our users, it's very unobtrusive. Our data scientists, they are tasked with doing data science. They shouldn't worry about any of the nitty-gritties of the lower stack of the infrastructure. And we want to make sure that we are getting out of their way and we are not imposing any barriers towards their productivity. And all of these have sort of borne fruit for us. So Metaflow has been in production at Netflix since the beginning of 2018. It has been battle tested. We have more than 600 projects currently live on Metaflow. Throughout this while, our data science team has actually only grown sublinearly, just adding a few people, while the adoption has been off the charts. Also, the time to production, what I mean here is that users getting some initial version to production so that then they can iterate on top of that, build on top of that, has been phenomenal. More than half of the projects see some version graduate to production within a week. So this was a brief summary of Metaflow, some of the principles, some of the learnings that we have had over the last few months as we built that. So very quickly, we spoke about how to reason about your machine learning workflows as functional steps chained together with an imperative shell, how scaling up and out and following a cloud-first strategy has been really useful for us, embracing reproducibility and focusing on an excellent user experience has borne fruit in terms of just internal adoption and the internal joy that we have sparked. So that's all, and I would invite any questions that you have. And one last plug, we are hiring. Reach out to us if you're looking for a job.
So if there are any questions, just raise your hand, and we have 2 mics, one on each side of the room.
Are you going to open source it?
We are thinking about open sourcing it.
Okay, thank you.
So Airflow is a workflow scheduler, and Metaflow also comes with its own Metaflow runtime, which is a very lightweight scheduler. So internally at Netflix, we use a different workflow orchestrator called Meson. And because all of these schedulers ultimately at the end of the day also execute some sort of a DAG, we export the user code in a form which is compatible with any of these schedulers so that our users don't have to reinvent the wheel and craft their code to make it compatible. Metaflow takes care of that translation.
Just curious, how does this kind of bespoke approach for kind of like enabling data scientists to iterate on their models compared to, are you aware of like Databricks MLflow, both the open source version and also the version they have?
So I'm only familiar with the open source version that they have, but I guess the execution model that we have is very different than what MLflow offers, just from a user's point of view. We take no assumptions around like what sort of machine learning model is being built. So we don't really work in the stack around like figuring out like how to piggyback on Keras or TensorFlow or any sort of thing. So I would say that these are two projects trying to solve similar problems, but in a different way.
Thank you.
Does Metaflow support dynamic DAGs?
Yes, it does.
Okay.
How are you versioning the notebooks, the Jupyter notebooks?
So that would be a question for our notebooks team. I'm not the notebooks team, but happy to talk about it later.
So in terms of side effect management, say, how do you handle the case like there is a function that takes time as an input, say they generate a random number based on time and that kind of things. So do you actually store the side effect as a metadata in some layers of the infrastructure, or so how do you deal with that case?
So when it comes to sort of like entropy in the system, right, there are two different things. One would be a user-defined entropy where, let's say, your code depends on time. So we introduce this concept of parameters, which we keep track of. But then if your code in itself has some sort of non-determinism baked into that, we don't really have a solution for that. And that was the entropy extreme of the reproducibility spectrum.
Yes.
Yes, please.
That was my exact question, is what are you guys thinking about for future for storing that entropy portion of it? Because obviously that's the next place to go for reproducibility.
Exactly. I mean, we are looking for people to work with us to solve that. Any more questions?
Sound like that's it. So I guess we'll wrap it up. If you want to chat with these guys, they're here. So lunch is now going to be served, so remember that.
All right. Thanks for coming.